Okay, awesome. So I'll be talking about question 1. And so basically question 1 is saying, consider the following reactions in which the elements A, B, C, and D are elements in their most stable state. And so A plus B gives Y, C plus D gives Z, and then the products of these two reactions will come together to give E. And it's asking you to draw out a thermodynamic cycle to describe the formation of E from the elements. So the first thing you'd want to ask when doing this question is, what is a thermodynamic sample or cycle? And so this is from the textbook. It's a set of reactions in which reactants and products are connected by two different pathways. The total free energy change along either pathway is the same, but one pathway may be more accessible to experimental measurement than the other. They allow free energy changes to be determined for processes that are conceptually important but difficult to study directly. So basically, there's two different ways to get from reactants to products, and we want to draw out the way that these connections occur. And so we're trying to draw a cycle to describe the formation of E from the elements. And what are the two different ways that E can be formed, each way using different elements or just molecules in both the variations. If anyone wants to chat what they think or say it, they can. Okay, I'll just tell you guys. So it's just given from this information. And so there's the most obvious way, which is just Y and Z. These aren't elements, but they're molecules. So Y and Z will give you E. And then the second is A, B, C, and D come together to give you E. And so again, we're just going to start with E because that's what we're trying to describe. So we're just going to place this kind of randomly, and then you want both arrows to be pointing towards E because you're going to be coming from two different ways. And so basically on either side of both of these arrows, there's going to be one of these two different ways. And so A plus B plus C plus D gives E, and then Y plus C gives E. And so then you have to find a way to connect A plus B plus C plus D. And so basically A and B gives you Y, and then C and D gives you Z. And so that's the drawing of the actual cycle. And then for portion B, it's asking, using the following table of delta G values, what is the value of the delta G for the formation of E? And so you should probably know this, is that delta G is the delta G of products minus delta G of reactants. And so in this case, it's Y and Z form E. And so the delta G for the formation of E is just going to be whatever it is for the formation of Y and Z and E. So it's just negative 100, which is the formation of Y, plus 120, formation of Z, plus 40, which is the formation of E from Y and Z. And that gives you 60. That's that whole problem. Yes, to the slide. This slide? I assume.
Yeah, thank you.
Okay. And then if anyone has any questions, you can ask them or chat. But that's the rest of the question. So I'll leave this slide up for a few more seconds and then. Okay. So whoever's doing question 2 can go.
Hello. Could someone make me co-host my iPad? Whoever's in charge of it.
Yes.
Thank you. Thanks. All right, so question 2 will be pretty quick. So it says that the difference in chemical potential for a specific molecule between region A and region B is 5 kilojoules per mole, and region B has a higher chemical potential. So to do A, all we have to know is that molecules spontaneously move from high chemical potential to low chemical potential. And basically what that means is that the molecules will move from B over to A, so the concentration of A will increase. And then part B says, what is the concentration in region A? So this is the formula we use. It's the change in chemical potential is equal to RT natural log of C2 over C1. But how do we know if C1 and C2 are concentration of A or the concentration of B? So the problem tells us that the change in chemical potential is 5 kilojoules per mole, which is a positive value. So that's a positive value over here, which means the right side of this equation also has to be positive. And that's only true if C2 is greater than C1. And we know that concentration of B is greater than the concentration of A. So C2 is actually going to be the concentration of B. So what we could write is 5 kilojoules per mole equals RT is given as 2.5 kilojoules per mole, natural log of 100 millimolar over X. And we're going to solve for X. So we divide 5 by 2 and 0.5, and then we exponentiate. We get E squared equals 100 over X millimolar. And then when you solve for X, you get 14 millimolar. And that's it for this question.
All right, there are no questions for question 2. I'm gonna go ahead and start with question 3. Okay, so for question 3, we're given a system of molecules of 2 types, which can interconvert. And we're asked a series of questions about the entropy of the system. So let's start with part A, which is asking what the entropy of the system is when it only contains one type of molecule, be that type A or type B. So let me remind you all of the statistical definition of entropy, which is that the entropy of the system is the Boltzmann constant times natural log of the number of states. And the thing to notice here is that we can just go directly to the answer from here, because in a system where there's only one type of molecules and all of the grid boxes are filled, there is only one possible state. So W is 1 and the entropy is just 0. So for part B, you're asked to derive the expression for the entropy of mixing. And you're asked to do this both using the statistical definition I just went over and the probabilistic definition. So just to start off with, we can already tell that this is, again, just goes to 0 from the previous part. So we're left being asked to show that the entropy of the state where it's mixed corresponds to this expression. So using the statistical definition of entropy, we can start off by writing that delta S mix is equal to KB ln of W, and then we want an expression for W. And since we know that there are, as given in the problem setup, n total molecules, of which Na are type A and B are type B, this is just equal to n factorial over Na factorial and B factorial. And this is just n choose Na or n choose NB. And then the last thing you'll need for this part of the problem is Stirling's approximation to simplify this into this form, which is just that the natural log of some number factorial is equal to n ln n minus n. And using that and your normal logarithm identities, you should be able to simplify this expression with this value of W to get this final answer. If you're getting stuck, also one more key thing to notice is that For example, XA is just equal to NA over N. So you can factor terms out conveniently to get this final expression. And then for the probabilistic definition of entropy, for the whole system, remember that that definition of entropy is just S is equal to negative N KB times the sum over all states of PI, ln of PI, where PI is just a probability of being in that one state. And then from there, we can get pretty quickly to our answer by noticing that since all boxes are filled, and each box must be either state A or state B, for any given state, like for example, for state A, it's just the number of molecules in state A over the total number of molecules. And you note that this is exactly equal to the mole fraction for state A. So just by substituting in the final expression that we want should fall out of this. And then for question C, it's asking what the difference is in chemical potential between two given states. So this difference, let's call this delta mu, is equal to the chemical potential at state 2 minus the chemical potential at state 1. And then from there, we can just calculate each of the individual states and then subtract. And one thing we can note from, I believe it was discussed in lecture, is that the chemical potential is just the free energy per unit molecule, especially since we're given to express our answer in multiples of kBt. So this would just mean that mu for a given state is just H minus T delta S over the total number of molecules. And we know that the two molecules have the same energy, so we know this term will cancel out in the final expression. So we know that our delta mu then must be equal to negative T times delta S mix for state 2 minus a delta S mix for state 1, since each of the states corresponds to one of the mixtures. So the change in entropy between both of them is just this subtracted quantity, and then divided by the total number of molecules. And then from there, you should just be able to simplify this answer out to your final answer using the same delta S mix expression that we got from the last problem and substituting the correct values for the mole fractions. And yeah, that's all for question 3. Does anyone have any questions? Oh, delta S mix 1 is just the change in entropy of mixing for state 1, where state 1 is given in the problem as having both mole fractions as equal, and you would just use the same delta S mixture expression that you got in part B of the problem.
All right, so for question 4, I'm going to share my screen. So we have a system that's similar to that described in question 3, except that there's a difference in energy between A and B, and there's no interaction between the different molecules. What would be the difference in molar energy if the molar fractions are 0.25A and 0.75B? So we know that A and B interconvert. And then the standard free energy change for this reaction is simply the difference in energy between pure B and pure A. And then since the entropy of pure A and pure B are basically the same, we know that the delta U naught is basically delta H, or the difference in energy between B and A. And we know that the mole fraction for A and B is 0.25 and 0.75. We can calculate the equilibrium constant is 0.75 over 0.25, which gives us 3. And now we just need to plug it into the equation. And we know that K is 3, and that gives us delta U naught as a negative RT log 3. And that's pretty much it for question 4. It's pretty straightforward.
Okay, I'll be doing question 5. Let me share my screen. You should be seeing my PowerPoint. Oh, okay. So yes, so for question 5, it's a similar premise to question 3, except you're adding in this gamma term, which will kind of be like the energy of mixing compared to just the entropy of mixing. This first term, of course, will be the same as the entropy of mixing, and for part A, you'll have gamma is equal to 0, so you're basically only looking at the entropy of mixing. And from here, you would expect that from an entropy only contribution that the free energy would be most negative when the mole fractions are equal. And when you plug in mole fractions into the equation given, you will find a graph similar to this. This is not perfectly to scale, so don't follow this graphic perfectly exactly, but it'll be something like this shape where you'll have basically a parabola-esque shape. Now for part B, you have gamma is equal to 3 kT. So now your energy contribution will be non-zero. And this energy contribution will also be positive because gamma will be positive. And oh, sorry, I did not change that part. But it should not say would be, oh yeah, sorry. Yeah, but your free energy will have two opposing forces now. So the entropy will be bring it down when the mole fraction is about equal, and the energy contribution will bring it up, more positive when the energy is about equal. And when you plug in numbers into that equation, you'll get a graph similar to this, where you'll have, instead of a dip in the middle, you'll have now a peak in the middle. And then comparing the two, if you compare the stable equilibrium points, you'll see that you only have one stable equilibrium on from part A, and you'll have two stable equilibrium points for part B. And in addition, this stable equilibrium point will be in the middle, where the mole fraction of A will equal 0.5, so which means that the mole fraction of B will also equal 0.5. And here you'll have a low mole fraction of A and a high mole fraction of B, and here you'll have a high mole fraction of A, a low mole fraction of B. And then if you think about that in like a physical sense, and you have some kind of solution or some kind of mixture of gases or in some aqueous solution, you'll have basically two compartments, two things that look separate in the same solution, where one will have the characteristics on the left of where you'll have a low mole fraction of A, and you'll have another compartment has a high mole fraction of A, and that should help you understand the phase separation. As another example, this is a graph comparing 3 kT versus 2.5 kT for gamma. This is the graph on the left is a 3 kT, and the graph on the right is a 2.5 kT. In the 2.5 kT case, you'll have the same two stable equilibrium points, but they'll be closer together to a mole fraction of 0.5, which means you'll be able to have a greater amount of mixing between the A and B molecules within those two separate compartments, which should help you understand how exactly the energy and the entropy compete against each other, and how having a lower energy of interaction, a lower positive energy of interaction, would allow for greater mixing while still having these two separate equilibrium points. And that should be all for question 5. Are there any questions?